Okay, so in the previous sections, we looked at how we can draw the Lewis structures for different molecules and even polyatomic ions. Now we're going to take a look and see how we can apply that to try now to describe the shapes of molecules, which we term the molecular geometry of a substance, right? So molecular geometry is just another term for just the shape of what that thing actually looks like. And this is important because the shape of the molecule will actually dictate several of the characteristics, both chemical and physical characteristics of the substance. Okay, so there's a reason why we kind of went through the Lewis structures step by step. We looked at the valence electrons, and we got those from the periodic table. We're then able to use the steps we described before to come up with the plausible Lewis structures. So now we're going to take a look at what these molecules actually look like. If you were to zoom in into a molecule of, let's say, a sample of water, for instance, H2O, what would that water molecule look like? Or a sample of methane gas, what would that actually look like? What would the methane molecule look like? So the idea of the shapes of molecules and molecular geometry is that we can predict them based on a model that we use quite prevalently called the valence shell electron pair repulsion model, and this is often abbreviated VSEPR. So, or VSEPR, abbreviated, or sometimes it's pronounced VSEPR. I know it isn't spelled that way, but that's sometimes how it's pronounced. Pronunciation. Okay, and this is based on our Lewis structures, and specifically, we're going to focus on the central atom, which is why that was one of the first steps in drawing our Lewis structures. Okay, so we're just going to look at that central atom, and then we're going to ask ourselves, how are the other atoms connected to it? The peripheral atoms, in other words. In other words, in what shape? Okay, what shape do all the atoms adopt? Okay, and that is what molecular geometry or shapes of molecules actually involves. So in order to determine how all of the atoms are arranged in a molecule, we first of all we need to look and see now, with that central atom, what exactly is around it in our Lewis dot structure. So the basis of predicting the shape of a molecule on the VSEPR model is that when you have electrons, as we know already, electrons are going to repel each other because they have similar charges, similar negative charges. And where are those electrons found around the central atom? Well, they are found in various domains, is a term that we're going to use. And again, we're just focusing now around just the central atom. We're not now concerned about the peripheral atom or atoms. We're just looking at what's directly around the central atom. Okay, so these domains, sometimes they're called electron domains or just domains in general. And these come in a variety of types. So we'll list these here. I'm going to list them, and we're going to count them individually. So a single electron domain can be any of the following. We can have a single bond. Okay, remember, a single bond is just a line. We can have a double bond, and a double bond counts as one electron domain. Double bond is two lines. We can have a triple bond. That also counts as one electron domain. Or sometimes you'll see electron group. Different books use different terms, but that's essentially what they mean. Or you can have a single electron domain being a lone pair of electrons, which is two dots. So any of these counts as a single, as one electron domain. Okay, and we're going to have to count those to determine now how are those electron domains going to arrange themselves. And they're going to arrange themselves in a very predictable way because they are going to repel each other. They want to be as far apart from each other as possible. They don't want to be close because they're gonna repel, right? So they want to be as far apart from each other as they possibly can be. So if we take a look at a couple examples, so here we have the Lewis dot structure for CO2. This is carbon dioxide. Okay, and again, we're just going to focus on the central atom, the C here. So around the carbon, we actually have a double bond, and we have another double bond. So that gives two double bonds, which counts as two electron domains. And again, it's just on the central atom. The peripheral lone pairs on the O, those are irrelevant when it comes to the shape of the molecule, right? The shape of the molecule, we're just going to focus on the central atom. In the case of ozone or 3, there's my central O. I have a double bond on one side, single bond on the other, and I have a lone pair. So I have a total of 3 electron domains. In the case of nitrogen in ammonia, NH3, I have a single bond, another single bond, another, so that's 3 electron domains plus the lone pair for a total of 4 electron domains. Okay, so that's how you want to count your electron domains. That's very, very important because the electron domain will actually dictate. So the number of electron domains will dictate the molecular geometry down the road, or the shape of the molecule. So we need to start, that's our starting point for molecular geometry. So electrons then, they will repel themselves to be as far apart from each other as possible in order to minimize their repulsive interactions. And again, if you think about why that needs to be the case, if the repulsions are minimized, that means that that's the most stable arrangement, right? And against we see this this phenomenon of stability inserting itself into lots of examples, lots of concepts. This is going to be a common theme throughout all of chemistry. So we want to minimize the repulsive interaction, so we have the most stable arrangement of the electron domains. So for instance, and you can actually build these electron domain geometries, right? So we have now the number of electron domains. We can use those to come up with, along with this simple fact, we can come up with what's known as the electron geometry, electron domain geometry. How are these electrons domains going to be oriented relative to each other? And you can grab some balloons and you can actually predict these just based on the balloons themselves. So if I have my central atom, let's say right here in the middle, so there's my central atom here. If I have 2 electron domains, right, the most stable arrangement would be to have them in a straight line, right? That's as far apart from as they can be from each other. We call that a linear arrangement. If I have my central atom, and again, central atom is in blue. If I have 3 electron domains, the most stable arrangement for those 3 electron domains would be a trigonal or sort of a triangular arrangement, and planar meaning that it's flat. And if I were to look at, complete the other one on the left side. If we were to look at the shape of this, it kind of looks like a triangle, right? And it's also planar or flat. If I have 4 electron domains, one may think that it should be a, like a square or something, but that actually is not the most stable arrangement. It needs to be in 3 dimensions. So if my central atom were here, the most stable arrangement is actually a shape called a tetrahedral shape. Okay, if you can imagine, it's kind of like a tripod with a head sticking out. If I have 5 electron domains, so there's my central atom, my 5 electron domains will arrange themselves in what's known as a trigonal bipyramidal arrangement. And you can think of that as having sort of a a central axis where there are two pyramids on top and on the bottom of that central axis. And we'll take a look at some of these down the road. So the last option here is if we have 6 electron domains around that central atom, well, then those will arrange themselves in what's known as an octahedral arrangement, as opposed to any of the other ones. So identifying how many electron domains you have around the central atom and using the VSEPR theory will allow us to come up with these different names for these electron geometry shapes. Okay, and that's the starting point for the molecular geometry, which is where we look at how the atoms are connected. So we sort of introduced several of these arrangements. We'll talk now about how we can now bring in just in addition to the electron groups, how we can bring in the atoms that we find in a particular molecule. Okay, so the electron domain geometry, which is what we just talked about, is how those electron domains will arrange themselves around the central atom. Right? Linear, trigonal planar, tetrahedral, trigonal bipyramidal, or octahedral. We'll list those here. Okay, so we have linear, we have trigonal planar. I'm going to abbreviate this as trig planar. We have tetrahedral. We have trigonal bipyramidal. And then we have octahedral. So those are sort of the starting points for determining the molecular geometry. And the molecular geometry now is where we just look at the atoms and how they are connected to the central atom. Because as you probably realize, not all of these electron domains are going to be connected to atoms, right? The bonding electron domains, single, double, and triple bonds will be connected to atoms, but the lone pairs, for example, right, they're not connected to atoms. There's nothing on the other side of the lone pair. That's why they're called lone pairs. So if we have, for example, different numbers uh, of atoms around that central atom, we're going to have these different types of shapes, all right? And when these atoms are connected, they're going to orient themselves, again, according to the VSEPR model, they're going to orient themselves to be as far apart from each other as possible to minimize repulsions. And as a result, they will adopt a certain bond angle between adjacent bonds, all right? So when we talk about bond angles, when we talk about geometry, we're looking at angles, etc. The bond angle is the angle between bonds that are right next to each other. So in a molecule like AB, where A is just an atom, B is just another atom, and the X here just represents the number or the subscript of how many of those peripheral atoms we have. Okay, so in our AB molecule, A is the central atom, and then B are the terminal atoms. They're on the outside, connected to the central. Depending on how many electron domains we have and depending on how many atoms we have, the shape of the molecule itself will be, we can use those two things to predict what that is going to be. We can also predict what the bond angle is going to be. So for instance, if I have my central atom here, we're going to put that in blue. And then I have my terminal atoms. If I only have 2 terminal atoms, so let's say I have a formula like AB2. So there's my A in the middle. And then the B's are on the outside. Okay. That shape then will be linear, and then the bond angle in a straight line, as you probably know, is 180 degrees. If I have another type of molecule where my formula now, general formula is AB3, so I have three B's connected to that central A in the middle. Okay, that shape is trigonal planar, and the bond angle there, if I take those three and I essentially separate it out, let's see, I get here, if I add them together, I get a circle. Circle is 360 divided by 3. The bond angle there is 120 degrees. This is this angle that we're looking at, right? The angle between the bonds. In a tetrahedron, which has a tetrahedral shape, that typically accompanies a general formula of AB4. So A is in the middle, and I have four B's around them, around it, sorry. That bond angle here is actually not 90 degrees. Okay, it's 109.5. So when you have structures like these, sometimes the way that we represent them is as follows. So this is my A, and I have my B's around it. This is how we usually represent a three-dimensional shape on a flat surface. Okay, we use different types of notations here. This bond that you see in as a dashed line, this one highlighted in yellow, that typically means that that bond is going away from you. And the bond highlighted in green, the one that's a solid wedge, this is meant to indicate that bond is coming towards you. Okay, that's the drawing system that we use in chemistry to illustrate three-dimensional character on a flat surface, like a screen or a piece of paper or a slide or something. And you'll see that throughout your textbook. All right, if we have an AB5 arrangement, something like this, where my central atom A is surrounded by five atoms. Okay, those five things will arrange themselves in a trigonal bipyramidal arrangement, and you'll see here that the bond angles are different. Okay, so the positions, I'm going to abbreviate, throw in some abbreviations here to illustrate the differences in the positions in the trigonal bipyramid. These positions here, along sort of the middle of it, these are known as equatorial positions. Okay, you can think of them as being along the equator, and that's an E that I just put in there. And the bond angles between the equatorial B's, or the equatorial bonds, okay, those are 120 degrees. And then on the top and the bottom, we can consider those as axial positions, sort of like the poles. Okay, and the bond angle between an axial and an equatorial is 90 degrees. And then as you can imagine, the bond angle between an axial and another axial, that's a straight line. That's 180 degrees. Okay, and that's going to be important for where electron domains would prefer to be if they had a choice to be an axial versus equatorial. We'll talk about that in a little bit. Okay, and then the last one here, octahedral. Okay, so octahedral, all of the positions, all of the 6 positions in the octahedron, they're all equivalent to each other. So this is A, B, and then we have 6 things connected to the central atom A. So we have 6 of those B's all the way around. So you can visualize this. Okay, the central atom here has these 4 B's that are kind of along and the middle, and then you have the terminal B's on top and the bottom as well. All of the bond angles here are equal to 90 degrees. Okay, all of these are the same bond angle. 90 degrees here, 90 degrees there. Excuse me, 90 degrees all the way around the octahedron.